Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 14, Profiling and Tracing. You are now watching Lesson 14.3, Micro-Level Optimization.
What I want to show you now is how to do a micro-level optimization. In other words, we're going to focus on a single function or maybe a couple of functions. And this might result from you doing a macro-level optimization, which we're going to talk about, but to do it at a micro level. Okay, so let's define the problem. So I wanted to learn how to use the I/O package. It's a package I don't get to work with very often, and it helps you stream data. So I came up with this idea. Let's take a stream of bytes, which I have here on the left between lines 23 and 35, and let's stream these bytes through our software, and anytime we see Elvis's name, like on line 24 here, not capitalized, we're going to fix it on the outgoing stream because, hey, he's the king, damn it, and we can't have his name lowercase, right? We're going to fix the entire internet with this little Elvis program. So in order to make sure the program's working and for us to write some tests and benchmarks, we've got a data table here with a streamed input and the expected output. And I've got some functions that assemble the streams into one big one. Now, let's just take a look at my algorithm. Now, I want you to remember something. I'd never done this before. Don't work with streaming data. So I just wanted to get something that worked, right? That's all I wanted to do. This is a draft of code. We're drafting code. So on line 83, I decided to put that stream of data that we're going to be working with in a buffer, a new buffer there, bytes buffer. We find the length of 5. I create a collection, right, a slice of 5 bytes, and identify at least that the first 4 is what we're going to need. So I come up with this end, right? It's also an ending index position for a slice, but really what I'm trying to do here is on line 93. I'm trying to read in the first 4 out of the 5 bytes out of the stream and put it into our buffer. If I can't even read 4 bytes, there's not going to be Elvis. And then I get into an endless loop, reading 1 more byte at a time, adding it to the end of the buffer. And then once I've got a full 5 bytes, I compare those bytes with Elvis. And if Elvis has that lowercase name, we replace it with the uppercase, and then we read another 4 bytes in. And if it wasn't Elvis, we just flush that byte out and we keep going, right? And you know, it took me about 20 minutes to write this algorithm, and it works, and I'm like super happy. So I reach out to the Go community and I say, does anybody else have a solution to this problem? Unfortunately, my friend Tyler from Salt Lake City provided me this. He says, Bill, you know what? I'm going to use a reader instead of the bytes buffer because all I have to do is read. And I'm also going to find the length there on 137. But what I'm going to do, Bill, is I'm going to create an index position there on line 140. And I'm going to read 1 byte at a time out of the stream. And once I read that byte, I'm going to compare what we're looking for, Elvis, lowercase e, L-I-V, right, with the current index position that I'm in. If it matches, I'll increment the index position. And Bill, if I get 5 matches in a row, in other words, we've incremented this index 5 times in a row, it's going to be Elvis. We're going to write out the replacement. If at any given time it's not Elvis, then we'll send out what we have and we'll unread it and we'll kind of reset and start it again. And I was like, Tyler, this is a pretty cool algorithm. And it works too. And so I say to Tyler, have you benchmarked this algorithm that you wrote? Because if not, I want to benchmark the 2 of them, kind of compare where we're at. And he said, no, Bill, I haven't really benchmarked it. So I went ahead and added an underscore test file. And I added 2 benchmark algorithms, one called algorithm 1 and one called algorithm 2. Now, notice what we're doing before the loop. We have a lot of work that's going to eat up, let's say, CPU cycles in memory as we assemble the stream. So what you'll notice on line 21 is the call to reset timer. Make sure you're calling reset timer before the loop if you're going to have a lot of work you're doing because you want to reset all those program counters. All right, great. So we've got algorithm 1 is mine. We've got algorithm 2 is Tyler's. I've got my benchmark functions in place. Now time to run the benchmark. So let's do that. So go test run, no tests, even though I don't have any. I just like to do that as habit. Let's see, we're going to run both benchmark functions. We're going to change the bench time to 3 seconds. And we also want to know about memory, so bench memory. Okay, so we're going to look at our allocations. We're going to increase the bench time to 3 seconds and run those 2 benchmarks. Let's see what we get. So algorithm 1 is mine. Algorithm 2 is Tyler's. And as this thing runs, we find out that my algorithm is running at 2,664 nanoseconds per op at 117 bytes of total allocation across 2 values that were allocated on the heap. So this is 2 values on the heap worth a total of 117 bytes at 226. We look at Tyler's algorithm and we learn a couple of things. One, his algorithm is running about 5 times faster than mine, and he wrote a 0 allocation algorithm. So I called Tyler up and I say, dude, you know you wrote a 0 allocation algorithm. Like, nobody writes 0 allocation algorithms out of the box. And he had no idea. So we were pretty happy about it. I mean, I was happy about Tyler doing that. And after I finished talking to him and I hang up the phone, I realized, you know, Tyler wrote a 0 allocation algorithm, but I didn't. And I really wanted to know where those allocations were coming from because, you know, he's like 5 times faster than me. If I could maybe get rid of those allocations, maybe I can get closer to the performance that he has on his algorithm. So I'm now at a point where I want to know where those algorithms are, those allocations are coming from. So how can I do that? Well, what we can do is run the benchmark again, but this time ask for a memory profile and write that profile to a file named p.out. So now what I'm doing is I'm running it again, but this time we're going to produce a profile, a memory profile for this benchmark that we're going to be able to look at. So there we are. He's still 5 times faster than me. I still have those 2 allocations. And remember something here. We're never going to guess. This is not about guessing. We're going to let the tooling tell us what the deal is, okay? We never, ever guess. All right, so I now have a p.out file here. So what can I do with that p.out file? Well, what I'm going to do with that p.out file is run the gotool pprof. So we're going to go gotool pprof. That's going to bring up our pprof tool. And I can simply just give it the p.out file, but there's something special you can also do if you give it the test binary that was produced. So when you go and you ask for a profile output like we did, the test binary that's built also hangs out, it stays around, and it's got that .test extension. So normally I wouldn't include the test binary with pprof. We're going to do it right now just so you can see something special when you do. Okay, so you can see here that the profile tool knows that this is the binary and also knows that we're in an alloc space mode. There's a couple of modes that you can be in for memory profiling. Alloc space is the most common because what that does is it says, show me all the allocations, whether or not they're still in the heap. You can also do alloc objects, right? So the number, not space, but the number of objects being allocated. And then the opposite of alloc is in use space, in use objects. So you can do all of that. Now, I'm in this interactive mode, and we already know that algorithm 1 is the algorithm that is allocating. So what I can do is use my list command and tell it, list any information you have on alg1. And you can see here that it found the algorithm 1 function. And what you can see here is that we see the 2 allocations. So there's an allocation on line 83. There's an allocation on line 89. Now there's 2 columns here that we should talk about. And this is the flat and the cumulative columns. Now, what flat means is that the allocation is happening here on this line inside this function. And cumulative means that the allocations are happening from this point of time in the code plus all other function calls down that call stack. So cumulative, sum it all up from this point down, or flat, which means it's happening right here. And we can see here that the profiler is saying that on line 83 that allocation is cumulative. So it's happening at some point down the call stack from this, but not exactly in this function. And on line 89, what it's saying is that there is an allocation, and it is absolutely happening here on line, or at least the the value is being constructed on line 89. That's really a better way to say it. It's saying that the value being constructed on line 89 is allocating, and on line 83 it's saying there is some value that is allocating within the scope of that call to new buffer. Now Go has another special command. I use the list command. If you do a web list command and also filter by alg1, it will bring up a browser version of list. And I'm bringing this up, and I'm running in 1.11, by the way. As we get new versions of Go, some of the tooling that I'm showing you, some of the displays change a little bit. This is one that might change over time. So I just want you to be aware of that. I'm in 1.11. But the web list view is showing something different than the console view. It's showing that on line 83, that's not just a cumulative allocation, it's also a flat allocation. Now this is really interesting. So why is the console view showing this only as cumulative, but the web list is showing it as flat? Well, that's because the web list view, at least in 1.11, defaults to a mode where the compiler optimizations are taken into account for the display. So the web list view actually is more accurate, at least in 1.11, as it relates to how the code really ran. The console view is showing you allocations that absolutely occurred, but the reasons would have been without the compiler optimization. So this is without compiler optimizations. That is what we have. That is with compiler optimizations. That is what we have. A little tricky, and the stuff can change a little bit. There's no real switch today, at least in 1.11, and not what I've seen in 1.12 that lets you choose the mode that you're in, and the language team likes the non-compiler optimized views for some reason. I don't know why, so you just got to be aware of that. Okay, now another reason I'm bringing up the web list view is, remember when I added the binary? So when you add a binary, you can go into the web list view and actually get this down to the assembly line. So again, I hope you don't need this. I really don't, but we can see that the allocations here are happening on this call to make slice. So we'll have to learn a little bit more in a second. So hopefully you don't need it down to the assembly line level. I've never needed it. Moving forward, I won't add the binary anymore, but I did want to show that. So what do we know right now? We know that this allocation on line 83 is really a flat allocation, which means that this value is being constructed here on line 83 and somehow allocating somewhere else. Now, we could sit here and guess where this construction is happening and where allocations are happening, but I don't want to guess. I want to know for sure. And what's nice is something that I had shown you earlier when we were talking about pointers is Go's compiler has the ability, if we use the right flags, to produce an escape analysis report. So instead of guessing what's going on here, let's run all this again, but let's add the escape analysis report so we can learn a little bit more. I'm going to clear all of this, and what I'm going to do is one more thing here. We're going to run this benchmark again, but this time I'm going to add the GC flags and the m equals 2. Now, this is going to produce an escape analysis report for the code that we're writing. If you need to go deeper into those call stacks, like into the standard library, you want m to equal 4. But since what we're looking at is just in our code, m equals 2 is going to be fine. All right, so I'm going to run this. Immediately, you see a bunch of things fly through the screen. That's our escape analysis report. We're going to need that. We're now running the benchmark again, and we're going to see those same results. We haven't really done anything yet. We see that he's still 5 times faster than us. Great. We now have that test binary. We also have the p.out file. So now we're going to go tool pprof p.out. There we are. We're going to get into our interactive mode for profiling. We're going to list algorithm 1. And now we've got everything we need in this one console window to figure out what's going on. Okay, so let's go and start with line 83 in the file stream.go. What I can do is hit Control F, type stream.go:83, and start looking at the escape analysis report. I'm going to scroll all the way up. And I notice once I scroll all the way up, we see our first report about line 83, and that says inlining call to bytes buffer. Inlining, okay. Things are starting to make a little sense now on why the optimized view showed flat and the non-optimized view shows just cumulative. Inlining is an interesting and really important optimization in Go. What inlining says is don't make the function call, just take the code out of the function and inline it in place. Now, there's going to be good performance gains that we can get from inlining, especially if functions are being called inside of tight loops. But there's other benefits as well. Let's go take a look at that line 83 in the source code to learn a little bit more. So here we are on line 83, and we can see the call to bytes buffer. Now, if we were to peek inside of bytes buffer, there's the implementation. It's literally just a return on construction. But I want you to notice something about this. This is using pointer semantics, isn't it? This is pointer semantic construction, which means, as we already know, that if you construct something and share it up the call stack, that is an automatic allocation. But we know that we're not doing that, right? We're not doing this call, that this call here got inlined. In other words, all of this code was taken out and the function call was replaced to look like this. There we go. And if no function call exists, then it can't be the function call, the fact that this factory function uses pointer semantics, that would cause an allocation, right? So let's go back and think about something. What did the inlining optimization just do? It removed the whole call, the whole function call. A function call that, if it was called, would have to cause an allocation because it's constructing and sharing. Because the call was inlined, the code was taken out and placed in, that eliminates the automatic allocation. Remember, when we look at this view of the profile, it's saying that the allocation is cumulative. It's assuming in this view that that function call was made. We know it wasn't. If it had been made, yes, this would have been a cumulative allocation. Now we know why the other view shows it as flat, because this function owns the construction, right? The construction is not happening inside of new buffer. It's happening here inside of alg1. So whatever's causing this allocation, it's going to be somewhere else in this code. So inlining is this amazing optimization because it does allow us to write factory functions that use pointer semantics without the automatic allocation tied to it. I mean, look at Tyler here. Tyler's working with NewReader. NewReader is a factory function that's also using pointer semantics, yet he has zero allocation. Why? Because this is being inlined as well. So Tyler is able to escape the allocation on that call because of the inlining optimization. So now we know that alg1 owns the construction of input. But let's go back to this escape analysis report. What I want to do is show you this line right here. If you notice this line, this is where the compiler is trying to make a decision on whether or not to inline the main function. And if you look here, it says cost 970 exceeds budget 80. What does this mean? So the decision to inline is really like a heuristic built on a point system. And if a function can score 80 or less, then it can be inlined. And there's a whole point system built into the compiler. I'm not going to get into it. But you can imagine, like, the construction of a slice could cost you 1 or 2 points. Calling a function inside of that other function costs you points. And any points that function's incurring causes you points. And so the idea is to have that score of 80 or less. And main is at the top of the food chain, so the chances of that being 80 or less are slim to none. But that new buffer factory function and the new reader functions, they absolutely were small enough to be inlined. So if you have a function that would benefit from inlining and it's scoring a little high, you can always come in here and then get a sense of what the score is, make some changes. But you're trying to reduce things. I can tell you this. If you want the best chance for inlining, especially with factory functions that are using pointer semantics, really make those factory functions leaf functions. Don't call any other functions inside of that. You can have the caller make the extra calls. You don't have to do everything in that one factory function. Having our pointer semantic factory functions inline is just great because you get the encapsulation without the cost. All right, so now we know that alg1 owns the input value, so there's still something else causing it to allocate. So we're going to keep looking. And then we come here. And this is literally saying to us that our input variable, our bytes buffer pointer, is escaping to the heap. And it's saying it's escaping to the heap because of something happening on line 93. Now, on line 93, it's saying there's an interface conversion and it's a call to a function. So let's not guess here. Let's go back into our code and find line 93. Here it is. And it's the call to read full. And if we dig a little deeper into read full, we notice that the first parameter to read full is the reader interface. We are passing a concrete pointer through this function call into an interface. And we had talked about this earlier. Anytime you store data inside of an interface, it's going to be an automatic allocation. So this is our allocation. This is why it's happening. It's a flat allocation happening here because we own it. Remember, that was inline. And the call to IO read full is accepting data not based on what it is, but on what it does. So now, if we take a look at Tyler's algorithm for 1 second, what I want you to notice is Tyler is not using the IO package at all. He's using the method set against input. And a method set, remember, is basically a function call going down the call stack. Even if it's using pointer semantics, it's sharing down. So there's no reason on line 145 for anything to have to allocate. Okay, great. So what we have to do if we want to get rid of these allocations then is take the approach that Tyler did. Get rid of the calls to IO and use the method set for input. And since I'm not tied to the IO package because I want to try to get rid of these allocations, we're going to do just that. So let's come in here and we'll come in and use the read method off of input. And what's nice is that it really has the same exact signature as that IO read. So we can literally come in here and get rid of these two calls. Boom. But we've got one more read call here, and that's trying to read 1 byte at a time at the end of the buffer. Now, that means we're going to have to do a couple things here. I'm going to have to declare my own error variable because what we're going to have to do is store that buffer. If I want to keep the algorithm the way I have it, right, then what we're going to have to do is this, and we're going to do the input.read byte, and that's going to let us bring that byte into the end of the buffer like we were doing. We can say if error doesn't equal nil, get all that, and we can pull all this code out here. I've just gotten rid of all of the calls to IO read that were asking for that input to be placed inside that interface value, which would have caused the allocation. So now, let's see what that allocation looks like. We should be from 2 to 1 right now, and hopefully we're a little bit faster than we were. So we're going to come in here, I'm going to exit out of this, I'm going to clear it up, and we're going to run it again with the GC flags. So here we are. Now hopefully we're down to one allocation. Where are we? Boom, there we are, 1 allocation. So we just got rid of one of those allocations for all those bytes. We actually shaved about 1,000 nanoseconds per op on that allocation alone. So now Tyler's only about 3 times faster, not 5. But we still have one more allocation here. So let's go back into the profiler. Let's list that alg1 and start looking at this. Now again, we're not going to guess. So Control F, stream.go 88. And what does the compiler say? It's saying that non-constant size. So remember another reason why the escape analysis algorithms would have to allocate is because if the compiler doesn't know the size of something at compile time, then it can't put it on the frame. Remember, those frames are fixed in length set at compile time. And we have a problem here. We have a make call using a variable named size. Compiler has no idea what the value of size is. Now, we could do something interesting here. If you don't tell anybody, since we're just focused on Elvis, I could hard code 5 here. Yeah, I know it's probably not the best thing to do, but if I hard code 5, now the compiler knows the size of the backing array at compile time. Since everything happens on this function, that should eliminate that next allocation. So why don't we try that now? Let's see if we get rid of the allocation. So here we go. Let's hope we're down to 0. And boom, there we are. We now have a 0 allocation algorithm, just like Tyler's. And now we got it down to about twice as fast. So Tyler went from 5 times to 2 times faster just by reducing those 2 allocations. Now, if we want to know a little bit more or try to improve this even more, then we're going to have to look at that CPU profile. So why don't we do the following now? We don't need the escape analysis report. We don't need a memory profile. I need a CPU profile. So let's add that, p.out. And now let's just take a look at, is there anything that we can do from a CPU perspective to get this any faster? I mean, I really like my algorithm. I'd like to keep it. Let's see what we can do here. So we're running the benchmark again. He's twice as fast as we talked about. Go tool pprof p.out. Now what you'll notice is that this is a CPU typed profile, so the compiler knows what profile it's reading. And then we can list algorithm 1, and we can look at this report, and we know that there's a 4.63 seconds of cumulative time here that we have to find. Most of it is cumulative, not flat. So we can look at these numbers and look for the big one. And here's the really big one, right? That's almost 3 seconds there on the call to bytes compare. Remember, Tyler doesn't use that compare function. He's indexing. So the reality right now is if I wanted to improve the performance of this algorithm anymore, the focus would need to be here. Again, we're not going to guess where to focus. We know where to focus. And the reality of all of this, to be honest with you, is that Tyler wrote such a good algorithm, we should just switch over to his, right? At this point, he just wrote a good one. We should do it. Which brings up one last point here. It's not necessarily a bad idea to have a couple people on the team write these algorithms in isolation. I love pair programming, but sometimes it's nice to just say, hey, let me see what your solution is. Let me see what my solution is. There's lots of ways to solve problems. And then we can have these 2 solutions like we did, and we can compare them. You know, we can compare them for readability, and we can compare them for performance and all of these things, and then maybe take the best of both and come up with a really great algorithm. So this is micro-level optimization in Go through benchmarks, doing memory and CPU profiling.